In this video, we are going to write a Python program for DFS. Let us look at the program. I'm going to walk you through the program. Look at it. I'm calling the function as DFS of A, init. A is the adjacency matrix and init is the initial node. So let us see how we do that. N equal to len of A. So A is the adjacency matrix. Find out how many rows are there. What is the length of A? That is called N. Now, to begin with, we have certain data structures. What are the data structures? Solution. Whether 0 has the solution, whether 1 has the solution, whether 2 has the... For each node, we must know whether that node has the solution. Here, since we want the algorithm to run the full graph, we assume that none of the node has a solution. So that is why solution equal to false for I in range of n. So this will make solution of 0 equal to false, solution of 1 equal to false, 2 equal to false, 3 equal to false, and the last one equal to false. Similarly, we want to keep track of what are all the nodes which are explode, for which I have a Boolean array, explode. Explode of 0, 1, 2, 3, everything is false initially. As and when we explore a node, we will make it true. Then we can keep track of what are the nodes we have already explored, what are the nodes which are yet to be explored. Similarly, in the tree that we are constructing, we have the level number of the tree, we have the parent relationship. So finally the DFS tree is a rooted tree in which init is the root, the initial node is the root. For all other nodes, for every node, there is a unique parent. So that is defined by this. Similarly, the path cost, all these things. Now we begin. Look at it. Line number 16, 17, 18. If solution of init, we are going to verify whether the initial node itself has a solution. If that itself has a solution, we will say print success and return the parent array and the path cost, because we will not do anything else. The initial node itself has the solution. Now we begin. Look, stack equal to init. So the initial node has been kept inside the node. Now parent node equal to stack dot pop of len of stack minus 1. See, the stack is a last in first out. So we will pop from the back. How will you identify the back? You find the len of stack. For example, if there are 10 entries in the stack, the len of stack will give you 10. So stack of 0 to 9 will be there. We have to pull stack of 9. That is why I am putting len of stack minus 1. So stack dot pop of the length minus 1. It means the last entry is pulled out. Last means there is only one way through which we are adding. We will add at the same side and we will also delete from the same side. So that is called the parent node. I have chosen the parent node. Mark it explode. Then it will have the children. So what we do is for I in range of n, so it will check one by one. All the nodes will be verified. What will be verified? A of parent node of I equal to 1. So we are finding out what are the nodes which are adjacent to the parent node. So in the parent node array, if you run from 1, 2, 3, 4 up to n, then see if A of parent node, so the row will be the parent node row, I. So I ranges from 0 to n minus 1. Then 1 if that is neighbor and it is not explored and it is not in stack. So there is an adjacent node, it is not explored so far, it is not in stack. If that is the case, add it to the stack. Stack dot append of I. So it will be added at the end. So we have added all of them inside. Now, after adding, what should I do? Now I am going to begin. So we are in the init node. For the init node, I have identified what are all the neighbors and I have put it. Now the iteration 0 starts. Iteration number 0, and before entering into the while loop, I can print the stack. So these are all for understanding of the algorithm. Now, this is the most important part of the algorithm. From line number 30, what am I going to do? Iteration equal to iteration. See, while the length of the stack is greater than 0, as long as the stack is non-empty, there are some entries there. Do the following. What is that? Iteration equal to iteration plus 1. Already iteration 0, now it is iteration number 1. So you print the iteration number. Now, what is child node? You pop. Because all the child node which are neither explode nor in the stack, all of them have been pushed into the stack. So now the child node we will have to pull one by one. So child node equal to stack dot pop of len of stack minus 1. So since it is a stack, we are pulling out from the back. Now what is to be verified? If solution of child node is there, then we are done. Otherwise, this is what we are going to do. What are we going to do? Parent of child node equal to parent node. So for this child, for the child node, the parent is now registered. Then the path cost equal to, so path cost so far plus 1, level equal to level plus 1. Now the child node is assigned to the parent node. Now the child becomes the parent. That is the depth first search. So in the depth first search, this is parent, now that is child. Now parent becomes child. So parent equal to child. Now print processing the node. Now what are the things to be done? Again, we'll have to do this checking. For that child, that has become parent node now. Now for the children of that node, find out what are the children, what are the adjacent vertices. If it is not explode and if it is not in the stack, then append it. Now explode of the child node equal to true. Then you go back to the while loop. So what we do is, initially we put all the children into the stack and come into the while loop. After coming to the while loop, each child is chosen, and then accordingly we explore, we verify whether there is a solution. If it is not, you take all the children, you push them into the stack, and then you pop, and then you proceed. Then it becomes the parent, and further you go there. So this is how the method is written. Look at it. Now in the main program, what am I going to do? I am going to consider, in the last video we saw an example with 15 vertices. Look at it. So for that, adjacency matrix is given as an input, and I am considering 0 as the vertex. Now I am going to run it. Look at it. Run. So this is the output. Look at it. Iteration 0. Before entering into 0, what are all the adjacent vertices of 0? 3, 4, 5, 6. Now when you pop, the last entry will be popped. So processing 6. So now the stack will have only 3, 4 and 5. Now what is the path cost? What is the level? What is the explode? Nothing. Only 0 is explode and 6 is explode. Then in iteration 2, 5 is explode. Iteration 3, 8 is explode. 10 is explode. So you can compare it with your walkthrough. This example I walked through in the previous video. You can compare these results with them. Look at it, 10, 11, 12. So finally, at iteration 14, explode equal to true, 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 true. All 14 are explode. And here is the parent. So for 0, 0 is the parent. Then 11, 14. For 1, 11 is the parent. For 2, 14 is the parent. For 3, 4 is the parent. So in a similar manner, this is given. You can verify this manually, which will give you a better understanding. So this is the Python program for depth first search. Thank you very much.